What is up, everybody? Welcome to Multivariable Calculus. This is also known as Calculus 3 in various schools, and usually is accompanied with analytic geometry as well, which is what we're going to do. Multivariable calculus is basically single variable calculus, or in colloquial terms, calculus 1 and 2, but applied to multiple variables, right? So you will not just be experiencing functions like f of x anymore. You will be experiencing functions with multiple inputs and spit out multiple outputs, and that's going to drive a decent amount of you crazy. It's going to drive me crazy, but fret not, because I'm going to tell you what you need to know before you start multivariable calculus. In fact, I'm going to tell you what you don't need to know, so you don't study for it, you don't dwell over it for a very long time. Now, things that you absolutely don't need to know is this, or things that you probably don't need to know are these things. Related rates. You don't need to know related rates. There probably won't be a question about related rates. Accumulation of change, also known as change plus accumulation, not integrals. Not integrals. You have to know integrals, but you don't have to know change plus accumulation, because it is very, very complicated. You don't need to know some techniques of integration. Some. You might need to know them depending on what class you take, but for the most part, the integrals that you do in Calculus 3 are not going to be that hard. There's something, it's probably going to be something like this, and it's not going to be that hard to integrate at all, because the integral of 3 is 3dx is 3x plus c, right? But if you have bounds, right, if you have bounds like this, then obviously it will evaluate differently. But the integrals that you get aren't going to be very complicated. The inside, right? So the inside won't be complicated. Maybe the outside will be. But you only need to know simple integrals most of the time. You definitely do not need to know improper integrals. And you don't really even need to know one-sided limits. You don't need to know how to do integral approximations like the left Riemann sum, the trapezoidal sum, the middle sum, the right sum. Right? You don't need to know any of that. You also don't need to know how to do the Riemann sum 1 over n whatever it is. I forgot. I actually don't remember it because it's that useless. I don't like to remember it. So yeah, you don't have to do any of that. You don't need to know series. It might come as a shock to many of you that you don't need to know series to do well, I guess you could say, in Calculus 3. But there's no series in Calculus 3 at all. You don't need to know certain approximation methods. You do need to know a linear approximation method, and maybe some quadratic approximation method, but you don't need to know all of them. You don't need to know Newton's method, or Euler's method, or Simpson's rule, which is, I guess, another integral approximation method. And you don't need to know volumes of revolution, because we're going to be doing volumes of many other things that are a lot more complicated than just a volume of revolution. So I guess that kind of means that you should know what a volume of revolution is, but we're going to be taking a totally different approach. We won't have a preset formula. We actually will have to work out what we want to take the area of, take the volume of. Now, these things you absolutely need to know from single variable calculus. The chain rule, right? I put the chain rule at the beginning because that's really important. You will struggle, you will fail the derivative section if you don't understand the chain rule. How to take the derivative of all elementary functions. So anything that you give me, I should be able to take the derivative of. I'm gonna put down a few problems right now. If you can't take the derivative of, you have to brush up on it. So let's say natural log of x squared over x, right? So that's one problem. E to the I'm sorry, that was bad. E to the x arc sine x. That's another problem. And we'll do one more. Xy plus x. This is implicit differentiation. So just find dy over dx. Find, I'm going to set y equals. Find dy over dx. Xy plus x equals y squared. There you go. So if you can find dy over dx for all of these three functions, then you are ready for Calculus 3. If you can't, you need to brush up on it. Optimization, you need to know the extreme value theorem. You need to know what makes something a maximum, what makes something a local minimum, what makes something a global maximum or absolute maximum, right? So you need to know those theorems. Second derivative test, you also need to know that. Integration, you need to know integration. I'm again going to put down 3 problems right now. If you cannot integrate it, then you need to brush up on it. So the integral of t squared plus 5t dt, the integral of from 2 to 5 of u times root of u plus 1 du, and the integral of from 3 to 6, or I'm going to say 3 pi to 6 pi of sine theta over cosine squared theta d theta. So if you can't take the integral of those three, you need to brush up on your trig. You need to brush up. Well, you need to brush up on your integration. You need to know vector valued equations, right? So I'm going to put down one problem. Find d dt of, is this in the screen? Yes, it is. Find d dt of 3t squared 1 over t natural log of t to the e. So if you can't do that, then you also need to brush up on your vector valued equations. Limits. Now limits, you do need to know limits. You have to know how to evaluate limits, but there's a little bit of a different way to evaluate limits. So even though you do have to know how to evaluate limits, the way that you evaluate limits in this case is not going to be much different. Sometimes you'll probably just end up using L'Hopital's rule a bunch of times. Now these are nice to knows. The next section, nice to knows. Continuity. You need to know you kind of need to know continuity, but there's a very different definition of continuity when we get into multivariable calculus, because you can be continuous, but you can have a hole in the middle. It's a little bit weird. Like, I'll explain once we get there. Squeeze theorem, you have to know. Squeeze theorems are nice to know, but squeeze theorem's a little bit weirder with 2 dimensions. You have to prove that in every single direction that the two functions are meeting closer and closer together. So squeeze theorem is a bit weird. MVT, curve sketching, L'Hopital's rule. I already told you about L'Hopital's rule. MVT and curve sketching, they're not really important because you're not going to really be able to draw a 3D shape, but they're nice to know. Displacement, velocity, acceleration, right? And more sophisticated integration techniques, like the ones that you need to use to evaluate stuff like this: x sine x dx, or the integral of 2 over x squared minus 8x plus 12 dx. Something like those things, right? Those integrals, they're kind of nasty. and you don't really like them, and they won't really appear that much in this course. Polar integration differentiation. Polar is good, but we're going to be using a totally different rule, and it's called Jacobians. We will still be messing with polar stuff, right? But it will be a little bit it will be a little bit more. It will be a little weirder, let's say. Differential equations, useful. We'll be usually we'll be dealing with partial differential equations, and it will be like really simple exercises. It won't be very complicated at all. You'll actually be dealing with a lot more complicated exercises when you get into your partial differential equations course, or your differential, like ordinary differential equations course. Vectors. Nice to know the vectors. You should have already done vectors in pre-calculus, and vectors are honestly more useful in the course of linear algebra, but it's okay to know vectors because you're going to be exposed to a little bit of vectors in multivariable calculus. Three-dimensional coordinate system. I don't know if you messed with 3 dimensions yet. You might have in physics, but it's nice to be used to the three-dimensional coordinate system, because we're going to be dealing a lot with the three-dimensional coordinate system in this course. Now these are all the things that we're going to cover, right? So the three-dimensional coordinate system and vectors are in there. Equations of planes, so you'll be able to figure out the equation of a plane in 3D space. Certain other 3D graphs, parametric equations, and vector valued, but vector valued equations are kind of summed up down here. Line integrals will deal with vector valued equations. Partial differentiations, complicated chain rule, the optimization curve sketching, Lagrange multiplier, Jacobians, multiple integrals, setting up multiple integrals, applications, average value and stuff, line integrals, evaluating line integrals, Green's theorem, Stokes' theorem, Gauss' theorem, or the divergence theorem, and surface integrals. And that's all we're going to cover. That's a lot of stuff to be covering in one semester, but you guys are 19 years old, 20, you guys are somewhere in between 17 and 20 years old by the time you take this course, so it shouldn't really be a big deal for you. You have been used to this level of rigor already, hopefully in high school, if not in your first year of college. So that will be it for the introduction. If you have any questions, please tell me in the comments below, or message me on Discord. And I will see you next time.